For 3 days in December 2004, the most dangerous object ever tracked by modern astronomy had a 1 in 37 chance of hitting Earth. And the people running the numbers couldn't tell you if it would land in the ocean, a desert, or a city. What they found 4 days later didn't just cancel the danger. It uncovered something we're still dealing with today. In December 2004, a 340-meter asteroid had a 1 in 37 chance of striking Earth. And for 3 straight days, nobody could say where. Not which country, not which ocean. The uncertainty region stretched across the whole planet, a band of possible destruction that could have fallen anywhere from a mid-Pacific fishing fleet to a European capital, and the astronomers running the numbers had no way to narrow it down. That asteroid is called Apophis. It never hit us. On April 13th, 2029, it returns. And this time, we know exactly what it's going to do. Pass within 32,000 kilometers of Earth's surface, closer than our own communication satellites, visible to the naked eye across 3 continents. What happened between the terror of 2004 and the spectacle of 2029 is a story about exactly how precise orbital prediction has become, and about the much larger, much less precise blind spot it's about to expose. Here is the number that matters most, so it's on the table before anything else. April 13th, 2029, 2146 Universal Time. Apophis passes 32,000 kilometers above Earth's surface. Geostationary satellites, the ones carrying weather data and television signals, orbit at 36,000 kilometers. For a few minutes, a 340-meter asteroid will be physically closer to this planet than the machines we use to talk to each other. Nothing this size has ever been confirmed to pass this close, on a trajectory anyone predicted in advance. That's the scale of the thing. Now go back to where it started, because the calm certainty of that number took 17 years to earn. Apophis was found on June 19, 2004 by Roy Tucker, David Tholen, and Fabrizio Bernardi, working from Kitt Peak in Arizona. They tracked it for 2 nights before weather and equipment problems cut them off, and the object dropped out of view. It resurfaced months later in data from a survey in Australia, and when astronomers combined the fragments of both sightings, the resulting orbit put Earth uncomfortably close to the middle of the uncertainty zone for April 2029. Within days, it carried a Torino scale rating of 2, then climbed. By December 27th, 4 days after the alarm first went up, the impact probability had reached its peak, 2.7%, roughly 1 chance in 37. No object, before or since, has ever been rated that high on a scale built specifically to communicate this kind of danger to the public. The name fit the moment. Apophis, the Greek rendering of Apep, the serpent that Egyptian mythology cast as the eternal enemy of the sun, the embodiment of chaos trying to swallow the world. For those 3 days, the fear wasn't abstract. Teams at the Near-Earth Object Dynamic Site in Italy and at NASA's own tracking systems were running independent calculations, checking each other's math, watching a number that refused to drop. The software itself struggled. Orbit determination tools built for routine near misses weren't designed for an object sitting this close to a real impact solution, and engineers had to adapt their systems in real time while the clock kept running. Nobody could rule it out, and nobody could pin it down. That combination, an asteroid capable of leveling a region and a threat corridor that could have touched almost any coastline on the planet, is as close as modern astronomy has come to a genuine global scare. It ended almost as fast as it began. On December 27th, the same day the probability peaked, someone found an older image of Apophis sitting unnoticed in survey data from March of that year. An accidental pre-covery, a photograph nobody had known to look for until they needed it. That extra 7.5 months of tracking history was enough. The orbit tightened, the impact solution for 2029 collapsed to 0, and within a year and a half, Apophis had fallen all the way to a Torino scale rating of 0. The 2029 threat was dead less than a week after it was born. But closing one door opened another, and this is where the story usually gets cut short in the retelling. Ruling out 2029 didn't rule out everything. Earth's gravity on a path this close doesn't leave an asteroid's orbit unchanged. It bends it, and there existed, somewhere in that 2029 flyby, a set of extremely narrow regions in space, some no more than a few hundred meters wide, where if Apophis happened to pass through one, Earth's gravity would redirect it onto a path that could bring it back for an impact years later. Astronomers call these gravitational keyholes. For the better part of a decade, the 2036 return carried a live keyhole risk. Then the 2068 return did too, and each one had to be individually measured and eliminated the same slow way the original threat was eliminated. More observations, tighter orbits, less room for the asteroid to be anywhere except exactly where the math said it would be. Radar measurements from Goldstone and Arecibo did the heavy lifting through the 2000s, and the final radar campaign in March of 2021 closed the case for good. Every known keyhole checked. Every follow-on impact scenario through at least the next century eliminated. Apophis was formally removed from NASA's Sentry Risk Table that year, and it has not returned since. This is also where the myths deserve to die, because the same numbers that closed the case are the ones that get twisted online. Apophis still gets linked, occasionally, to Wormwood, the star of the apocalypse from the Book of Revelation, as though a naming decision from a discovery team in 2005 was somehow prophetic. It isn't. The name came from an ancient god of chaos because the asteroid briefly deserved the association, not because anyone involved thought they were watching scripture unfold. And the residual fear about the 2036 and 2068 returns, the idea that this thing is still secretly circling back for us, doesn't survive contact with the actual data either. Every keyhole tied to those dates has been individually measured and closed using direct radar ranging, not modeling, not statistical inference, physical measurement of where the asteroid actually is in space. The math that once put 1.3 billion square kilometers of uncertainty on the table now places Apophis's 2029 position to within a few kilometers, more than 4 years ahead of the event. The object that terrified 2 independent tracking centers in 2004 is, today, one of the best characterized asteroids in the solar system. None of that makes April 13th, 2029 uneventful. It makes it something rarer, a genuinely safe encounter, precisely enough understood that 2 space agencies built missions around watching it happen. Picture what an observer actually experiences that night, because the flyby isn't a single moment. It's roughly an hour of something no human being has ever watched before. In the hours before closest approach, Apophis is already crossing the sky faster than any airplane, faster than the International Space Station, a point of light climbing in brightness as the distance closes. Around 2035 Universal Time, it reaches its peak, briefly rivaling the stars of the Little Dipper, easily visible without a telescope to anyone under a clear, dark sky across Europe, Africa, and large stretches of Asia. Then the real strangeness starts. Because Apophis is so close, it doesn't crawl across the sky the way distant objects do. It moves. Trackable motion, visible against the background stars in real time, faster than the width of the full moon every 60 seconds. Somewhere on the ground, someone is watching a 340-meter asteroid slide past overhead with nothing but their eyes, at a range closer than the satellites carrying that night's weather forecast. And then, within the hour, it swings into daylight and disappears, headed back out into the solar system on a bent, permanently altered orbit. That altered orbit is not incidental. It's the entire reason 2 space agencies are spending hundreds of millions of dollars to be there. Earth's gravity, at 32,000 kilometers, is strong enough to physically stress a body this size, and scientists modeling the encounter expect measurable effects: a shifted rotation axis, a changed spin rate, quite possibly landslides and seismic shaking across the asteroid's surface as internal stresses redistribute. Nobody has ever observed that process directly on an object of this size, while instruments were already in place and watching. That's the scientific opportunity Apophis represents, and it's why NASA and the European Space Agency each built a mission specifically timed around this one Friday afternoon. NASA's contribution is OSIRIS-APEX, a spacecraft with a history already attached to it. Under its original name, OSIRIS-REx, it traveled to the asteroid Bennu, collected a sample of its surface material, and returned that sample to Earth in 2023. Rather than retire a spacecraft that still had fuel and instruments in working order, NASA redirected it toward Apophis, renaming it along the way. OSIRIS-APEX will arrive shortly after the Earth flyby and spend roughly 18 months in close proximity to the asteroid, mapping how its shape and rotation have changed. The most technically demanding part of the mission is a maneuver engineers call the Surface Time-Constrained In Situ Reconnaissance, or STIR, in which the spacecraft descends to within about 5 meters of the surface and briefly fires its thrusters downward. The exhaust plume kicks up loose material that has never been exposed to sunlight, giving scientists a look at subsurface composition without the cost and risk of a landing or drilling mechanism. It's essentially an improvised excavation tool, built from a spacecraft that was never designed to do this. Repurposed because the opportunity arrived faster than a dedicated mission could have been built. The European Space Agency's answer is RAMSES, the Rapid Apophis Mission for Space Safety, and its defining feature is timing rather than technique. Where OSIRIS-APEX studies the after, RAMSES is built to capture the before. It launches in 2028 and arrives at Apophis in February 2029, a full 2 months ahead of the flyby, giving scientists a detailed baseline of the asteroid's shape, spin, and surface features before Earth's gravity has touched it at all. RAMSES reuses a substantial amount of hardware and engineering from ESA's earlier HERA mission, which studied the aftermath of NASA's asteroid deflection test at Didymos, a decision that let the agency compress what would normally be a decade-long mission timeline into roughly 4 years. RAMSES is expected to carry at least one small CubeSat companion, deployed to attempt closer observation or a landing attempt during the encounter itself, adding a second vantage point to whatever the main spacecraft records. Put those 2 missions together, and something genuinely new emerges. RAMSES documents Apophis exactly as it is beforehand. OSIRIS-APEX documents exactly what it becomes afterward. No asteroid encounter in the history of spaceflight has ever been bracketed this precisely, a scientific before and after photograph of a world being reshaped by another world's gravity, backed up on the ground by radar facilities like Goldstone running continuous observations through the entire encounter to cross-check what the spacecraft record. Here's the harder question sitting underneath all of that engineering, the one that actually matters once the fireworks are over. Apophis is not a discovery story. It's a recovery story. It scared 2 independent tracking centers half to death in 2004, and then it took 17 years of dedicated observation to fully clear it. That's the system working exactly as intended. Patient, thorough, expensive, and it applies to an object we already knew to look for. The uncomfortable truth is that the same size class of asteroid, somewhere between 100 and 300 meters, the range capable of leveling a city or a region depending on where it lands, remains substantially incomplete in our survey catalogs. Estimates of how many objects that size are still undiscovered, still on orbits nobody has computed, run into the thousands. Apophis became world famous because we found it decades early and had time to argue about it in public. The asteroids we haven't found yet don't get that courtesy. They get discovered, if they're discovered at all, with weeks or days of notice instead of decades, and by definition, nobody is tracking a keyhole for an object that hasn't been spotted. That's the real inheritance of April 13th, 2029. Not the naked eye spectacle, though that alone would be worth the wait. Not even the unprecedented before and after study of a gravitational encounter, though that data will reshape how planetary defense models are built for years afterward. The inheritance is proof of concept, a demonstration on the largest and most public stage astronomy has ever had, of what it actually looks like to find a dangerous object early, watch it long enough to be certain, and turn a near miss into decades of usable science instead of decades of anxiety. The system did that for one asteroid we happened to catch in 2004. The open question the flyby leaves behind isn't about Apophis at all anymore. It's about how many more objects in that same size class are out there right now, unfound, on orbits nobody has had the chance to argue about yet. We'll be tracking the radar campaigns as they refine the encounter through 2027 and 2028, both missions' launch and arrival windows, and the flyby itself as the date closes in. Watch the sky.